In this video, we will demonstrate a lightweight application that allows for classification of land cover types from Sentinel-2 data. The application was developed at University of Maribor. Since it is still in work progress, please contact the authors for further information. The basic idea behind the approach is to exploit the differences in the reflectance characteristics of different land cover types with respect to wavelengths, or so-called spectral signature, measured at a single pixel of Sentinel-2 images. As Sentinel-2 is a multispectral instrument, it is capable of capturing spectral signatures at 13 different wavelengths, or so-called spectral bands, with the resolution ranging from 10 meters to 60 meters. On one hand, this allows users to derive a number of different indices that may reveal valuable information about the state of vegetation, water, terrain, or a number of other spatial entities. In our case, we use this information to do completely automatic recognition of land cover types. However, spectral signatures do not depend only on the spectral properties of the land cover types themselves, but also on the lighting condition in which they are recorded. In this context, shadows are a typical example that may cause partial or even total loss of the spectral information, which may result in large classification errors. In the first graph, spectral signatures of different land cover types under shadow and non-shadow conditions are shown. It may be observed that in general, lower intensities are recorded in shadows in comparison to non-shadow areas. Perhaps two spectral signatures of forests are the most obvious example. However, a closer look reveals that spectral signatures of shadowed meadow is almost identical to that of the water. This phenomenon is also known as overlapping of spectral signatures. Especially since single land cover type may produce many different spectral signatures, as this can be seen in the second graph, land cover identification is a difficult task. In continuation, we will show how this is achieved using machine learning approaches. Our implementation was done in C++ with the help of libtiff, OpenCV, and SIMG open source libraries. But first, let us download the data. For this purpose, we use Copernicus Scientific Hub. For this purpose, we just write Copernicus Scientific Hub into Google and click on the first link. We then select Scientific Hub. We can then log in and zoom to select the area of interest. We select the area of interest by drawing an orange rectangle and then just click search to see what data is available here. Amongst many available datasets, we just search for Sentinel-2 data and click on the URL associated with it. The downloading process will then start. The download data will be in TIFF format, so you can use it in any GIS tool that you usually use and also split it to smaller tiles to make it easier to handle. In our case, all of this will be done by the algorithm automatically. First of all, the data will be divided into smaller tiles, and the second derivative of the spectral signature at each pixel will be automatically calculated, because such representation is much more robust to shadows and other type of noise within the data, as you can see on the graph on the right side. Several additional information will then be calculated, such as co-occurrence metrics from image contrast, energy, and homogeneity can be retrieved. This information helps greatly in computer understanding of what is the content of the image. The algorithm is designed to learn itself what is in the image, and it does this in several iterations through the process known as boosting. This makes our classifier very easy to use, as only 2 clicks are required. First, the user must run learning process. This can be done by clicking on Learn button or by loading pre-learned knowledge. Let's say that we will run a learning process, so we click on the Learn. After each iteration, a message box shall appear with the report about how much the algorithm has learned in terms of the accuracy that it can achieve. Although it starts with the overall accuracy of 77%, it can reach 88% in one iteration. The main reason for this is that the algorithm has now learned to process large shadowed areas. In the next iteration, the accuracy of the algorithm reaches about 91%. Here, smaller shadows and soft transitions between shadowed and non-shadowed areas are coming into focus. During the next iterations, the progress of learning will become slower, because the algorithm is focusing more and more on the details. When the algorithm will achieve 95% accuracy, it will stop and will be ready for using. Now we can select the data that we would like to process and process it by clicking on Classify as To button. In few seconds, a new TIFF image will be created in the same directory that will contain classified land cover types. Here are some examples of classified images where red represents build-up areas and brown represents farmland. Blue represents water and light green represents meadows. Dark green represents the forests. So hopefully this video demonstrated how land cover information can completely automatically be extracted from Sentinel-2 data. While the authors will continue to develop algorithms on Sentinel-2 data, including image deshadowing, multitemporal land cover monitoring, and change detection with integration of Sentinel-1, you are welcome to contact them for any additional information. Thank you very much for your attention.